Welcome to this video on the role of kernels and system configuration in computing, specifically across IBM per Mega-Siemens DOS, Windows, and Linux. At the heart of any operating system is the kernel, which acts as the core interface for hardware and system resources. Complementing it is the system nervous system, a collection of configuration settings that tell the kernel how to operate. In DOS, the kernel is notably small and sequential, focusing on one task at a time. The system settings are stored in simple, human-readable text files that are easy to modify. The DOS boot process is straightforward. The BIOS initializes hardware, loads the kernel into memory, then processes the configuration files config, sys, and autoexec.bat to set up the working environment. Key files for a DOS boot include the kernel itself, command interpreters, and the vital configuration files that act as the system's nervous system. DOS offers the advantage of being lightweight and fast on older hardware with an open configuration style. However, its limitations include restricted memory protection and the inability to handle multiple tasks simultaneously. Moving to Windows, we find the NT kernel, which manages complex, multitasking operations with robust security. Its configuration is handled by the registry, a centralized binary-based database. Windows booting is more elaborate, involving the boot manager and BCD to locate system files. Once the kernel and hardware abstraction layers are loaded, it initializes the registry to configure the entire system environment. Essential components for a Windows boot include the boot manager, the BCD store, the core kernel executable, and the registry files located within the system configuration folder. Windows excels in multitasking and broad device compatibility. Its main drawback is the closed, complex nature of the registry. If it becomes corrupted, the entire system can fail to operate correctly. Linux provides a highly flexible and open kernel. Its system configuration is organized within the /etc/ directory, where various text-based files manage specific system functions. The Linux boot sequence begins with grub, which loads the kernel and initial RAM disk. The kernel then mounts the main file system and reads configuration files from the /etc/ directory to prepare services. Key files for Linux booting include the grub configuration, the kernel image, and the initial RAM disk, while the /etc/ directory serves as the primary hub for system-wide settings. Within the /etc/ directory, you will find critical files that control everything, from partition mounting to user permissions, passwords, and administrative access rights. Finally, subdirectories within /etc/ handle specialized tasks, such as managing network interface configurations and automated system services, providing a modular approach to system management. Beyond basic configuration, Linux features other vital files in the /etc/ directory. These include settings for terminal environments, DNS resolution, system identity, and login messages. All of these are plain text, making them easily readable without specialized tools. One of Linux's greatest strengths is its modularity. Because the kernel is open source, you can modify it to remove unnecessary features, add support for custom hardware, or optimize it for specific tasks, such as server or embedded use. The /etc/ directory is equally flexible for system-wide adjustments. To modify the Linux kernel, begin by preparing your environment with essential development tools. You will need to download the official source code, extract it to your workspace, and always create a backup of your current kernel and system to ensure safety. Once prepared, use the "make menu config" command within the source folder to open a text-based menu. Here, you can decide which features to keep, remove to save memory, or compile as separate modules that can be loaded or unloaded as needed. After configuration, you compile the source into a functional kernel using make in your processor's available cores. This step is followed by compiling your chosen modules and installing both the modules and the new kernel into the system. To finalize the installation, update your bootloader configuration with update-grub and restart your computer. You can then select your newly built kernel from the boot menu to test its performance. While kernel modification can lead to a lighter and faster system, it carries risks. Incorrect settings can cause boot failures, so always maintain backups and, if you are a beginner, practice on a virtual machine first. After the kernel starts, the system initialization process takes over to launch services. Traditionally, this was handled by sysvinet, a sequential system, while modern distributions now use systemd, which is faster and manages processes in parallel. Sysvinit uses a classic approach with run levels and the /etc/init tab file to manage boot states. It relies on scripts located in /etc/init.d/ and specific directories like /etc/rc0.d/through /etc/rc6.d/ to start and stop services. In the sysvinit model, the kernel initiates the process designated as init, the first process to run. This process then reads the init tab file and executes the defined scripts in a specific, ordered sequence. Modern systems use systemd, which treats services as units. Configuration files for these units are found in /usr/lib/systemd/system/4defaults and /etc/systemd/system/4 user-specific overrides. You manage these services using the systemctl command. When the kernel boots with systemd, it triggers the systemd process as process number 1. The system then automatically reads the unit configurations within /etc/systemd/system/ to initialize and organize all services. Comparing the two, sysvinit is simple and relies on readable shell scripts, though it can be slower due to its sequential nature. Systemd is more complex but offers greater speed, dependency management, and parallel processing capabilities. While systemd may seem more complex for beginners, both systems remain highly configurable. As part of the Linux nervous system, they both store their primary settings in the /etc/ directory, allowing for complete control over system behavior. Today, systemd is the standard for most major Linux distributions, including Debian, Ubuntu, Fedora, and Arch. In these systems, you will find that managing services is centralized through the systemctl command and unit files stored in /etc/systemd/system/system/. While many distributions have adopted systemd, several remain dedicated to the traditional sysvinit. These include Slackware, which maintains long-standing traditions, Dev1, which was specifically designed as a systemd-free alternative to Debian, and versions of MX Linux. These systems utilize files like /etc/init tab and services in /etc/init.d/. Some distributions offer flexibility by supporting both initialization systems. MX Linux allows users to choose their preferred method during installation or boot, while Gen 2 defaults to OpenRC but officially supports switching to systemd. Additionally, Linux from scratch gives users full control to choose between them when building their system. It is also worth noting that even in distributions where systemd is the default, such as Debian, there is often continued support for legacy sysvinit scripts. Systemd is designed to be backwards compatible, allowing it to execute older service scripts to maintain operational stability. To summarize, computing environments have evolved from the simple text-based configurations in DOS through the complex, centralized binary registry of Windows to the highly flexible and distributed text-based /etc/ structure that defines the Linux nervous system. Thank you for watching this video. If you found this information helpful, please like, share, follow, and leave a comment below to let us know your thoughts.